Let's consider 11th problem. You can read over here and let me explain what it says. It says that there is a bar which is uniform and it is fixed at these two ends, and you are pulling by a certain force like this. Now this force is gradually increasing. When you keep on increasing this force, there is a value called F naught. When it reaches to F naught, which is 150 Newton, then this bar breaks. And then after you take the same bar, connect with two identical masses. These masses are of m value. The bar is of m naught mass, and you apply a force again on the center and increase this force. And these two masses have been connected by a string. We need to find what the maximum force this can be so that this bar doesn't break. And this picture has been placed on a frictionless horizontal surface. It's a good question. So the first figure and the second figure we need to connect. Now when this breaks, so basically it is the limit of its material strength, and we need to connect that material strength at this location or the second case. So let's try. Solution. Now in the first case, if we look at it, this F naught force is breaking it. So if we draw the free body diagram of this bar in the first case, you will find the F naught, when F naught force acts over here, F naught force acts over here, it breaks. Now any force acting at the center will be balanced by the two forces coming on this. You can call it as a T. They are going to be equal. Now this T is going to be equal to F naught by 2, or you can say the total T is going to be equal to this total force. But this tension, this is not going to describe the strength of the material, the breaking process. So if we look at the breaking process, so if we visualize this kind of situation, these 2 points are fixed and you're pulling it at the midpoint, then you'll find it's going to break. Can you think from where it's going to break? It's going to break from the midpoint, yes. And even in that midpoint, if I enlarge this or magnify a bit thickness, this bar thickness, let's say this was like this, and somewhere here this breaking is going to be there from the midpoint. And in that breaking you'll find, let's say this is 1 point, this is 2 points, so this 2 point is going to open first. And then opening will start, keep on taking like this. So these two upside and downside, they will get detached. So that's how the breaking is going to be. And then finally a point will also break, so it will become in 2 parts. Anyway, so we need to check the strength, how much the forces, inner forces are stronger. So we can say, let's say we draw the half of it, free body diagram of half of it, some sort of this, and let's say it's breaking from somewhere, this, and here is acting a force T, this one. So T is acting on this top point. Let's say we call it as a T naught. So 2 T naught is going to be equal to F naught, so T naught will become F naught by 2. And you'll find that this F naught will be shared in the 2, so this will be acting on this as well. So here also it's acting F naught by 2. Moreover, about this point it is going to turn. Let's say this, about this 1 point is going to turn. We can think of this this collective force that is describing the strength is acting at this location. Now it can act effectively. It can act at anywhere in this thickness. We can catch it anywhere. Like we are considering at this point. It's okay. We can consider at any distance x as well. So here I am considering, let's say this gap or the thickness is d, or at a d distance, the total effective strength force is acting. For now, if torque acting on this about this 1 point can take over this force or torque of this force, then material will say it's not able to connect these 2 points, or that means breaking has started. So breaking case, what is going to happen? So condition we can frame from there. Breaking case, or just breaking case, you say the forces are balanced. Breaking case will be when this, we can say this torque about it, that will be of F naught by 2, this force and this distance. Total length is this L, so this we can think of this total length is L, so this is going to be L by 2. We can say this is going to be L by 2. If this force is greater than, or this torque is greater than or equal to this T into D, the torque on this direction. So this torque is trying to retain the shape, whereas this is going to break it. So that is breaking case. Limiting case, so for limiting case or just break case, we can write it as the T, the strength should be equal to, or let's write as a T into D should be equal to F naught L by 4. So this is going to the situation, right? This is the strength of the material we are talking about. Now let's come to the figure number 2. This was the for figure number 1. Now in figure number 2 we can solve the first we can solve it like this, that this is moving with acceleration, so it's going to carry certain acceleration. The force is being applied at the center point F, and there's a block which is connected over here, there's another block connected over here. This got mass m naught, this got mass m, this got mass m. We can say this is moving with acceleration a. So simple equation, the total force is equal to mass into acceleration, so F must be equal to m naught plus twice m times a. Basically from here we are able to find the a for acceleration, which is F divided by m naught plus twice m. This is going to be the acceleration. Now we need to see this half portion of the bar. So let's draw the free body diagram of this half portion of the bar and magnifying its strength, this width. So we are magnifying the width as well. So here it's going to be certain tension acting. Let's say this tension is T dash. So this is going to be T dash. And whatever the force we are applying, half force will be contributed to this or given to the upper half. So it's going to be F by 2. Moreover, we are drawing this free body diagram of the bar with respect to bar itself, so that bar remains stationary, right? So we are watching this in a stationary condition. So you'll find there's going to be a pseudo force acting at the center of this, and that pseudo force is going to be the mass of this bar. Whatever the sample we have taken, it's m naught by 2. We have taken half of it into a for acceleration. Now again, this one point we are interested in, and we will say that just limiting condition, breaking condition, this effective tension or strength force will be T. This distance is still the D. So the condition would say, like, at one point the torque which is trying to break it must be balanced by the torque which is holding it. So we can say T, this is holding torque, is going to be equal to T dash into L by 2. That's going to be act at a distance L by 2, of course, plus m naught by 2 into A. This is a pseudo force which is going to act at a half of the distance or half of its length, which is L by 2, and again dividing by 2, that is L by 4. Now this TD and this TD has to be equal because they are related to the strength. So we can say if we know the T dash, so we can relate these two. Now how to get the T dash? Again, we can make one more equation, draw the free body diagram of this particle. So this particle is going to be pulled by T dash, and it is moving with a acceleration. So T dash is basically m into a. Later on we can place this value of a. So this becomes t dash ma L by 2. Sorry, this t dash is ma, so I should replace this t dash. It's going to be ma L by 2 plus this is coming m naught a L by 8. If you want, you can take a L by 8 as a common. Within the bracket you will get like 4m plus m naught. Now what is a is given to us? We can substitute there, and we can relate this equation with this equation. So combining the two equations together, we will find like this: f naught L by 4 is equal to a. A can be written as f, then divided by m naught plus twice m into L. There is L as well, and there is 4m plus m naught. From here we can find the value of f. So this f is going to be equal to, now this 2 will be there, 4 will get cancelled out with this m, and this 2 will go this side, so it will become twice f naught, and this denominator will go upside, which is going to be like m naught plus twice m divided by, when you divide this, so you will find in denominator will become this number, which is m naught plus 4m. So this is the maximum force that you can apply on this bar in order to this is moving safely, that is, it's not breaking. Now we can put the values, and if we put the values of f naught, m naught, m, all are known to us, you can check in the question, and if you find put these values, simplify, you will get its answer, numerical answer, which is going to be as 200 Newton. You can check that. That's a simple point, you can check easily. So that will become your final answer. Let me tell once more: f naught has to be placed as 150, small m has to be placed as 5, and m naught has to be substituted as 10. So you'll get your answer. Okay, so this is overall solution for this question. Thank you.